Hi, this is Arindam from the School of Chemical Sciences, NISER, Bhubaneswar. Very welcome to the lecture series on the hydrogen atom problem. This is lecture one of the series where we'll start formulating the theory of hydrogen atom. The hydrogen atom problem is actually a two-body problem. We have one nucleus and one electron. But this two-body problem can easily be converted into a single-body problem, and we'll quickly see that how that can be done. So imagine a coordinate system represented by x, y, and z, correct? And two particles, m1 and m2, having position vectors r1 and r2, which is given by these expressions. So the x1, y1, and z1 are the coordinates for particle 1, x2, y2, z2 are the coordinates for particle 2. And now let's define two more vectors. One is this R, and this is capital R. So the small r vector is defined in this manner, where the coordinates x, y, and z are represented as the difference of the x coordinates and y coordinates and z coordinates of the two particles. It means that this x, y, and z, they represent the distance between the particles. That is why this x, y, z coordinates are known as the relative or internal coordinates. So this vector small r, or rather its magnitude, is the distance or the separation between the two particles. Now the other vector capital R represents the position vector for the center of mass for these two particles. Obviously, the center of mass has to be on the line joining these two masses. So therefore, this capital X, capital Y, and capital Z, they are coordinates for the center of mass. And from classical physics, we know that this capital X, capital Y, and capital Z are given by these expressions. Now, this two defined vectors, capital R and small r, are definitely related to the original vectors R1 and R2, the position vectors for the two individual particles. And let's quickly check how these four vectors are related, because that relationship is important as we move forward. If you just use the expression for this capital X, capital Y, and capital Z into the expression for capital R, we get these large expressions. And if we just rearrange these terms a little bit, we can easily show that capital R and the position vectors R1, R2 are related in this manner. Capital R is equal to M1 R1 plus M2 R2 over M1 plus M2. And the small r is rather easily correlated with R1 R2. Small r is just R2 minus R1. Now that we have found that these four vectors are related, so the system of two particles can either be represented by the position vectors R1 and R2, or by the defined vectors capital R and small r. We know that for an n particle system, to represent the movement of all the particles, we need 3n number of variables. That is the degrees of freedom for that particular n particle system. Now for two particles, it is 6. So here we need 6 independent variables to represent completely the movement of these two particles. Now we can have two sets. We can choose any of the two sets of 6 variables to represent the system. And those two sets of 6 variables are, the first one is the x1, y1, z1, x2, y2, z2, the position coordinates for the two particles, or capital X, capital Y, capital Z, the coordinates for the center of mass, and small x, small y, small z, the relative coordinates. Any of these two sets we can use to represent the system. Now, next, what we'll do is that we know that how to write the Hamiltonian in terms of these position coordinates. But now what we're going to do is that we're going to write the same Hamiltonian using these coordinates. We know that it is possible because as these two sets are related, so writing any function with these, if that is possible, it is definitely possible that we can write the same function using these. So let's go ahead and write down the Hamiltonian in terms of this center of mass coordinates and the relative coordinates. So the Hamiltonian H has two parts, the kinetic energy part and the potential energy part. So we will try to write both the parts using the coordinates of the center of mass and the relative coordinates. But let's start with the kinetic energy part first. If we define the velocity of the particle 1 as v1, the vector v1, which can also be written in terms of the position vector of particle 1, dr1 dt, or in short, we can write r1 dot. Similarly, we can define the velocity of particle 2 as r2 dot, and then we can write down the kinetic energy of the total system, which is the kinetic energy plus of particle 1 plus the kinetic energy of particle 2 in terms of this r1 dot and r2 dot as T equals half m1 r1 dot mod square plus half m2 r2 dot mod square. So this is basically half mv square and half m2 v2 square. And we can use the property of vectors that for any vector A, for example, the mod square can be written as the vector dot product with itself, and using that particular property of vectors, we can write down the kinetic energy again as half m1 r1 dot r1 dot. So this is the kinetic energy of particle 1, and similarly this is the kinetic energy for particle 2. So this is the total kinetic energy for the system in terms of r1 dot and r2 dot. Now the next thing that we have to do is that, as you know, the relationship between r1 and r2 with capital R and small r, will replace these r1 dot and r2 dots in this expression to get the kinetic energy of the whole system in terms of capital R and small r. So I have plugged in the expressions for r1 and r2 in terms of capital R and small r, and I have taken the dots appropriately, and therefore we get the first part, which is the kinetic energy of particle 1 as the half m1, and this entire thing is r1 dot and dot product with again r1 dot. And similarly for the kinetic energy of the particle 2, we get half m2, and this is the whole expression for r2 dot and the dot product with r2 dot again. Now we can certainly rearrange these terms a little bit, and then the terms will be simplified. Few terms will just drop out, a few it can be simplified. And once we do that, the kinetic energy of the system takes the form as below. So I have written down the total kinetic energy of the system in a slightly simplified manner. I have taken out first the capital R portion. So capital R dot capital R becomes capital R square along with this m1 plus m2, the total mass of the system. And then we have two additional terms like this, which can further be simplified and put into one single term as this one. And now if we define capital M as the total mass of the system, which is m1 plus m2, and if we define another variable mu as this quantity, m1 m2 over m1 plus m2, then we can write down the total kinetic energy of the system as split into two parts, one part involving the mass of the total mass of the system, m, and another part involving the reduced mass of the system. This mu, this quantity, is known as the reduced mass of the system. So we have got two kinetic energy terms involving into the total or summing up rather into the total energy of the system. Further to that, if we now define the two momenta, one involving the capital M, another involving this reduced mass mu, as these quantities, so therefore capital PM is capital M capital R dot, and the P mu is mu small r dot, then we can write down the kinetic energy of the system, that means these two parts, as the Pm mod square over 2m and P mu mod square over 2 mu, and this is the total kinetic energy of the system in terms of the coordinates of the center of mass and the relative coordinates. Now let's go to the potential energy, and then we'll formulate the total Hamiltonian of the system. Now let us talk about the potential energy. Here we'll be taking one assumption on the potential energy, that the potential energy or the potential of the system depends only on the separation of the two particles. It simply means that the potential V depends only on the relative coordinates or internal coordinates. What are the examples of such potential? Two quick examples are: one, the Coulomb potential between two charged particles. The Coulombic potential energy depends only on the separation of these two charged particles. And second, the gravitational potential energy that depends on the separation of two masses. If this happens, if this is the potential, this is the nature of the potential, then we can write down the total Hamiltonian in the following way. So we have two kinetic energy parts, the Pm square over 2 capital M and the P mu square over 2 mu. And then we have the potential part, but as we have already discussed, the potential depends only on the relative coordinates. So therefore, this whole part that is becoming a function of the relative coordinates, we have just bracketed them here. And now we get this particular situation that the total Hamiltonian, which depends on all 6 variables, are split into two different Hamiltonians. One we have written as H capital M, that depends only on the capital R, that is the coordinates of the center of mass, whereas there is another part. This part depends only on small r, that is the coordinates which are the separation coordinates or the internal coordinates. So as there are no terms in the Hamiltonian which involves both capital R and small r, so this system turns out to be a system where there are two hypothetical particles, one having mass capital M, another having mass mu. They are coexisting. And we know that if that happens, then we can have two independent sets of Schrodinger equations, right? One involving H capital M, another involving H mu, and we can solve them this way, right? So if you have so the energies like E capital M, that is the energy of the particle, hypothetical particle of mass capital M, and similarly the energy E mu for the particle mu. And and this particular situation, we know that the total energy E, if we call it that E, that is just going to be the sum of E capital M plus E mu, and the total wave function, if you like to write it this way, it can be easily written as the product of those two individual solutions, individual wave functions. Right? This is a property of a system when the Hamiltonian can be split into two independent Hamiltonians involving two different sets of variables. Now let us discuss what these two equations actually mean, what they represent, which type of motion do they represent. So let's talk about this equation first, which involves the coordinate capital R, which is the position coordinate of the center of mass C, and mass M, the total mass of the system. And this equation doesn't have any potential term. It simply means that this motion is like a free particle like motion, because free particle also doesn't have the potential term. V equals 0 you can put, or V equals constant you can put. Now this equation simply means that the whole system along with the center of mass is moving freely in space. And this is something that we will not be so much interested when we'll go to the hydrogen atom problem, because if you imagine now this particles M1 and M2 are basically, one is a nucleus and other is an electron. This motion simply means that the whole atom as a whole moving from one point in space to another point in space. And this movement, well, it will have certain kinetic energy, and this kinetic energy can be anything. For a free particle, there is no discreteness in the energy spectrum. So the energy spectrum is an absolute continuum. But nonetheless, this is not so interesting. What is interesting is the motion governed by the other equation, and that equation is this one. This gives the relative motion of one particle with respect to the other. Why is it important for an hydrogen atom? Because a quantity like this will simply give us the probability density or probability distribution of the electron as a function of its separation from the nucleus, because this small r is the relative coordinate, the position of electron relative to the position of nucleus. And such quantities are we are interested in, the probability distribution and its energy as a function of its separation from the nucleus. These are the important things that we are looking for when we'll be doing the hydrogen atom problem. So next, when we are going to the hydrogen atom problem, we'll not be interested so much to write this equation and solve it, but we'll be writing this equation. And for writing that equation, first thing that we need to do is that we need to know the exact form of this V. And once we know the exact form of this potential V, we can write the Hamiltonian and then we can solve it. And then we'll be getting the energy of this electron as a function of, again, as a function of its separation from the nucleus, and the wave functions as a function of small r, which is the internal coordinates. So let's start the discussion on a hydrogen atom from the same picture that we had drawn previously for a two-body system. The only difference that I have tried to make in this picture is that I have made this one particle much bigger than the other one, which is the case for an hydrogen atom, because the nucleus is way larger and way heavier than the electron is. So here the M1 is replaced by the capital Mn, the mass of the nucleus, and the M2 is replaced by Me, the mass of the electron, and the ratio of these two masses are like this. And if we have this ratio in hand, then the mu, or the reduced mass of the system, turns out to be pretty close to the mass of the electron, and therefore we can safely assume that the reduced mass mu and the original mass of the electron Me are pretty much same. In other words, we can assume that the mass of the nucleus is infinitely heavier than the mass of this electron. So what will happen is, although technically we should use mu, the reduced mass of the system, for the equation involving the internal coordinates, as we have seen previously, but instead of doing that, we'll be keep on using Me with this particular notion in mind, that it is just a slight approximation. If we really need the eigenvalues and eigenfunctions accurately, we should replace Me by mu. We can also check what happens to the coordinate of the center of mass. See, although I have drawn it in this particular fashion, the same way as I had drawn previously, but quickly we can check where the position would be. So I have replaced this R1 and R2 by Rn and Re for obvious reasons. And then using those, if we try to calculate the position coordinate of the center of mass, we get something like this. So it is 0.0005 Re plus 0.9994 Rn, which is pretty much Rn. So it simply means that the center of mass is same as or this particular capital R, this purple vector is pretty much same as this Rn. That means the center of mass is actually sitting on top of the nucleus because the nucleus is much heavier. So we're going to assume from now on is that this not only it is much heavier, but it is kind of infinitely heavier. It simply means that in this two body motion, the nucleus doesn't move at all. The center of mass is exactly on top of the nucleus. The movement is all about the movement of this electron with respect to this static nucleus, which is sitting at one particular point in space. And if we assume that, what we can do is that we can redraw the coordinate system. We can shift the origin of the coordinate system on top of the nucleus, and then we can simply use the internal coordinates small r as the position vector of the electrons from the nucleus point, because that is what it is defined as. So here I have redrawn the coordinate system once again. Now the origin is coinciding with the nucleus, which is assumed to be infinitely heavier than the electrons, and therefore all motions of the nucleus is ignored. It is static, it is infinitely heavy and static, and it is sitting exactly on the origin of the coordinate system. So therefore this electron is now the only particle in this two particle system which is moving, and its movement can be represented using this position vector r. So this r is the same internal vector that we were talking about in the two body system. Now as one particle is not moving, the center of mass is therefore exactly on the origin. So therefore the movement of this particle can be tracked, can be represented by this position vector r, that can be written down as this, the magnitude of r times the r caret, which is the unit vector along r. And we can write down the potential to start with using this internal vector as a v of r or v of x, y, z as this. So this is a simple Coulombic potential. It is a Coulombic attraction between the negatively charged electron and a positively charged nucleus. So the charge on the nucleus is plus Ze. We can write down the charges if we wish. So the charge on the nucleus is plus Ze, and the charge on the electron is minus E. So therefore we get a minus Ze square on top, and then we have 4 pi epsilon 0 r as the denominator. We can write down in terms of x, y, z as well if we wish. Now this is the potential that solely depends on the separation between the nucleus and the electron. The situation that we were discussing, that if that particular thing happens, then we can use certain properties that we can now describe the entire motion of the system in terms of this internal vector r, and that is exactly what we are going to do also in this situation. We can quickly calculate the force that is acting on this electron due to this nucleus. This is going to be an attractive force, and the force is given by the negative differential of the potential. If we take care of the fact that we have a negative sign over here, which will cancel with this negative sign, and then if we take the differential of v with respect to r, we will get back this negative sign again, and this is going to be r square. This was r, and the potential is going to be r squared. So it's an inverse square law. We know that the Coulombic attraction force is the inverse square force, and the direction of the force is going to be along the minus of r caret, which is in the opposite direction of the r. So therefore, the force is going to be acting on this direction. So this is the direction of the force, and which is obvious because we have two charges which are on opposite nature. One is a positive charge here, another is a negative charge here. So this Coulombic force is going to be attractive. It is obvious that the force that this electron is going to be experienced due to this nucleus is going to be towards the nucleus. It's going to be attractive force, and that is exactly what is coming because of this negative sign along with this r caret. The direction of the force is becoming towards the center. We can also write the total energy in terms of the internal coordinates x, y, and z. So this way, so we have px square, py square, and pz square, whereas px, py, and pz are the three components, x, y, and z components of the momentum of this electron, and we have the v, x, y, z already written here, and there's the E is the total energy. Now we can use this expression for total energy, and we can make the operator form of this equation. Then we can use operators for the potential and the operators for the total energy, and then we can get the time dependent Schrodinger equation ready for the hydrogen atom. And the solution to this Schrodinger equation is going to be a psi, which is ideally is going to be a psi of both space coordinates x, y, z and time coordinate, right? And we can use the fact that our potential is not an explicit function of time, right? So this is a function of space, obviously, but this is not an explicit function of time. So using this particular fact, we know that we can split this particular psi further into two parts, and we can write down these two parts as the space part and time part. So we can write down this portion as some space part, which is going to be a function of the x, y, and z, and the time part is going to be like e to the power minus I e t over h cross. We know that, right? And this space part is what we'll be getting out of the time independent Schrodinger equation, which I'm going to write next. So here is the time independent Schrodinger equation. We have used the Laplacian operator, which has this particular form in the Cartesian coordinate. And we can write the Hamiltonian separately, which is obviously in the left-hand side here as well, as the expression like this. Now, we know that the potential is given by this particular Coulombic term, having this x square plus y square and z square over here. Now the question is, can this Hamiltonian, which is a function of x, y, and z, be split into three Hamiltonians? Each one of them is a function of only one variable. The reason I'm asking this is that if we somehow can write the Hamiltonian in this particular form, where you have h1, h2, and h3 involving only one of the coordinates, in that case, the solution to this equation, this wave function psi, can also be written in a nice way as a product of three functions, each involving only one variable, like this. This is a very convenient form, and thus three different parts of the solution can easily be found using the method of separation of variables of differential equations. But for that, as I told previously, that we need to split the Hamiltonian into three different Hamiltonians involving only one variables. Now the Hamiltonian has this particular part, which is the kinetic energy part, which has a nice x plus y plus z form already. So there is no problem splitting this kinetic energy part into three different parts involving only a single variable. But the potential part has this x squared plus y squared plus z squared over here, and there is no way that this particular potential v x y z can be split into three different functions involving only one single variable. So as a whole, the Hamiltonian, which is a function of x, y, z, cannot be split into three Hamiltonians in the Cartesian coordinate. So what's the solution? The solution is that we will not be using Cartesian coordinate. We'll switch over to the spherical polar coordinates, where we'll see that this problem will not exist at all. There, the potential as well as the kinetic energy part, all the parts, the entire Hamiltonian, can be split into three different Hamiltonians involving single variable. In the spherical polar coordinate, r theta phi, we do not have that problem that the potential is involving all three coordinates, because in spherical polar coordinates we can represent the potential in terms of r only. But now, if we have to use spherical polar coordinates, we have to use the form of the Laplacian in spherical polar coordinates. And the Laplacian in spherical polar coordinates is given by this expression. On a first look, it might seem that now the Laplacian cannot be split into three coordinates r, theta, and phi because of terms like the r square and sine theta are coming along with the theta operator and the phi operator. But if we look at properly that the operator part, which is the r operator part and the theta operator part and the phi operator part, they are separated. These extra terms can easily be managed, and it is going to be possible to split the Hamiltonian into three different Hamiltonians involving only one variable. The first one involving only r, the second one involving only theta, and the third one involving only phi. And therefore, in spherical coordinate, we can get a solution of this wave function as a product of three different functions, each involving only one variable, and therefore we get the solution of this form, where this capital R is the R part, the capital theta is the theta part, and the capital phi is the phi part. Now, next what you need to do is that you have to find out these three different functions separately by solving three different differential equations coming out of this original differential equation involving this Laplacian in spherical coordinates and this potential in terms of r, and then we'll get our solution for the hydrogen atom problem. So if we just insert the expression for psi, which is the product of three different functions, into the original differential equation, the original time independent Schrodinger equation, we get this expression. Now, if we notice closely, you'll find that we have not used the partial derivatives anymore. That's the reason is that when the solution is of this form and we are having only this particular operator of r operator, right, then the theta and the phi part acts just like a constant. It comes out of this operator, and then this operator is involving only a function of r, right? And hence we really do not need any partial derivative anymore. So I am absolutely free to use the total derivative, and that is exactly what I have done. Similarly, in the theta part, as this theta part, we have this theta function over here. Then the r and the phi function came out of this operator portion as constant, and similarly here we have the r and theta came out, and we have only capital phi in this operator part. And the v is the potential. You have the entire psi, right? So this r theta phi is the psi, and then the right hand side is the e, and then r theta phi. Now this equation can be simplified a little bit, and we can then proceed uh, towards solving this equation. Now, if I multiply both sides by minus 2m r squared sine square theta by r theta phi h cos square, then we rearrange the terms a little bit, we get something like this. Now here what we see is that the left hand side is a function of only phi, whereas on the right hand side the variable phi doesn't exist at all. So whenever you have situations like this, that the left hand side and the right hand side are involving two different sets of variables, then the only solution to this situation is that both sides are equal to some constant. So now if we just equate both sides equal to a constant, and the constant that we are going to take is equal to minus ml square. So the why you have taken such an odd constant? The reason behind this is that if we take this particular form, the constant is minus ml square, then the value of ml that will be obtaining after the solution are going to be the good numbers. Good, what do you mean by good numbers? They are going to be integral numbers, right? If we take any particular constant, then the values that are going to be obtained after the solution are not going to be so nice. So that this particular form is purely based on experience. By convenience, we have taken this particular form, but the concept is that the left hand side and the right hand side, as there are no common variable, so therefore the both sides should be equated to a constant. Now if I just take this particular portion, the left hand side is equal to the constant, then we get our first equation involving the function capital phi, and that equation is this. This is the equation that we will have to solve for getting the phi part of the solution out. But now we can use the right hand side as well, which is also equated to the same constant ml square, minus ml square, and we can do a little bit of rearranging, and we can get from the right hand side being equal to minus ml square another set of equation, and that is given by, once again, we have got a situation where the left-hand side is the function of only r, and the right-hand side is the function of only theta, along with, obviously, this ml square, the constant that we have assumed previously. But nonetheless, we have, again, the similar situation that the right-hand side and the left-hand side are not sharing any particular variable, and hence both sides should be equal to, again, another new constant. This time we'll take this constant to be equal to L into L plus 1. That's the constant. Now we could have easily taken the constant to be just L. In that case, the values of L that one would get after solving are not going to be nice numbers, nice values. If we take L into L plus 1 as the constant, whatever it is, then the values of L that we will be getting are nice values. So again, both this minus ml square here and the L into L plus 1 here, this is the choice of these two constants are purely from experience, purely from the point of view of convenience, nothing else. Any particular constant could have been taken, but it does just because we want finally the value of ml and the value of L to be nice ones, we have taken these constants. Now we have already got one equation for obtaining the phi part, and now here we'll be getting two equations, one for the r part, another for the theta part. What you have to do is that you have to equate this left hand side to this constant, and you have to the right hand side to this constant, and these two will give us two more equations involving only the capital R and the capital theta. So therefore, we'll be getting set of three equations, one for each functions, and those three equations are our next step, that we'll be solving them one by one and to get the total solution. But before going to the solution, let's list down all the equations that we have obtained. Just list them in one page, and that should be kind of the end of this lecture one. So here is the list of the three very important equations for each of the functions: the capital phi, the capital theta, and the capital R. That would ultimately constitute the total solution for the hydrogen atom problem. Now, it is important to note here that here in this R equation, we have the potential over here, correct? So this particular separation of variables worked because now the potential is just a function of R. Had this been a function of R and theta and phi combinedly, we could not have achieved the separation of variables that we have done so far. We could not have achieved to get three different equations for the three different parts of the solution. So what we are supposed to do next? What we should do is that we should solve these three equations one by one, and then we should get the solutions, which are the functions capital phi, capital theta, and capital R, and then we should plug them in here to get the total space part of the hydrogen atom problem. So we'll start solving from equation 1, and we'll see that after solving, only certain values of ml will give acceptable solution. By acceptable solution, I mean acceptable quantum mechanically. Now we'll take those allowed values of ml and we'll plug them in here, and we'll try to solve the second equation. Once we do that, we'll find that only few allowed values of L will give acceptable solution for capital theta. We'll take those acceptable or allowed values of L, we'll plug them here, and then we'll solve the third equation, and then we'll get all three parts of the wave function. We'll just simply write them in this product manner to get the total space part of the hydrogen atom problem. So I'm finishing the lecture 1 here. We'll move forward to the lecture 2 with these equations, and we'll solve them one by one.